We live in a world of data that we can't see. A single word embedding in a modern LLM might have 768 dimensions, but our human intuition hit a hard ceiling at 3 dimensions. We cannot visualize these 768 dimensions. So, is it possible to project the data from high dimension to some low dimension d' by keeping as much information as possible, like projecting a sphere in 3-dimensional plane to a circle in 2-dimensional plane? PCA does this by keeping as much covariance structure as possible, by keeping orthogonal directions that discriminate well the points of the cloud. PCA is often called a dimensionality reduction technique, but that's a boring way to describe it. PCA is actually a change of basis. It's the mathematical art of rotating your high-dimensional data until you find the perfect shadow, the one that captures the most information. Suppose we have a data in 3-dimension plane and it is mostly covered by the principal component shown in red and green, but along the third principal component, the data is not spread out. Turns out we can project the data on these two principal components and show the same distribution in a 2D plane without losing much information. Now we will walk through one example and see how PCA works. Suppose you ask some of your friends to rate on a scale 1 to 10 4 different foods. First, we center our data. We find the average rating for each snack and subtract it from everyone's score. For example, if the average samosa rating is 5.5, Aman's score of 10 becomes 4.5. This centers our food cloud at the origin. Now we calculate the covariance matrix of this mean centered data, which is calculated by the formula mentioned. Look at Aman and Ananya. They both love samosa and dosa but aren't a big fan of pani puri. Saurabh and Piyush are the opposite. This suggests samosa and dosa are correlated in our dataset. The covariance matrix captures this friendship between features. So the diagonal values shows the variance and the off-diagonal values shows the covariance. Now for the next step, we will find the eigenvalues of this covariance matrix, which is calculated using the characteristic equation determinant c minus lambda equals to 0. After getting the raw eigenvalues, we will sort the eigenvalues in the descending order. The largest eigenvalue will cover the most variance. Now to get the direction, we will first find the eigenvector of the corresponding eigenvalues. Consider for lambda 1, we solve the equation c minus lambda 1 ix equals to 0, where x is the eigenvector corresponding to lambda 1. After solving for x, we will get our first principal component. Similarly, we can get principal component 2, 3, etc. Now the main question arises, how many principal components we need? For that, we'll first calculate the explained variance, which is nothing but the particular eigenvalue divided by the sum of all eigenvalues. For PC1, explained variance is around 88.7%. Similarly, we will calculate the explained variance of all the eigenvalues. Let's plot these variance on the graph. Our target is to get the cumulative variance around 95%. Which is, we want to select the dimensions that can capture 95% variance of our original dataset distribution. In this particular case, the first two eigenvalues is sufficient to cross the threshold, so we can safely represent the data in 2 dimensions. In the last step, we will project our original data in 2 dimensions. For that, we will multiply our centered data distribution matrix with a matrix W, in which the columns are the eigenvectors corresponding to the top 2 eigenvalues to get x projected. Let's plot these values on each data points on the graph, where the top 2 principal components will be our new axis. Now this new plot will tell the same story as our original data distribution. Recall, in our original dataset, Aman and Ananya have similar taste, which is also visible in this 2-dimensional plot. Now let's generalize this idea. We have some data x with n data points and m features. We will first calculate the covariance matrix C, which will be m cross m. Then we will find the eigenvalues corresponding to this covariance matrix and sort them in descending order. We will select the top k components, which will cover at least 95% of the variance. We will arrange the eigenvectors corresponding to these k eigenvalues in a matrix W. We will then multiply our original data matrix with this W to get new distribution with at most k important features. Note, we kept all n data points but reduced the features from m to k with maximum variance retained. Hence our dimensionality is reduced. So I hope you understood the PCA well.